All right, our final video here, going through some of the examples dealing with centripetal force and acceleration. So we have the outer edge of a 120 millimeter diameter CD-ROM, experiences an acceleration of 1.6 meters per second squared. Determine the velocity of the edge of the CD. So, an idea, dealing with the CD-ROM, and we have an acceleration, and the acceleration will be inward of 1.6 meters per second squared, even though I put 2. So 1.6 meters per second squared. So what do we know here? We know our acceleration. That'll be centripetal, 1.6 meters per second squared. And that'll be in. We know the diameter, which means we got to convert the radius. So 120 millimeters, that's 0.12 meters. Divide that by 2 to get it to a radius, so 0.06 meters. And that's all the information we need if we want to find the velocity. And what we're looking for is this velocity at the outer edge. Okay, so from our centripetal acceleration formula, we would have v squared over r. Rearranging it, v is going to be the square root of centripetal acceleration multiplied by r, so the square root of 1.6 times 0.06, and we end up with 0.31 meters per second, and it will be, in my diagram, it's going to be up. All right, so therefore, our velocity is 0.31 meters per second up. Okay, so there we go. That is one example of using the formula for centripetal acceleration. Second example, we have a 0.2 gram flea, and on the outer edge of a 10 centimeter spinning disc, the disc RPM, revolutions per minute, RPM is 80. Determine what centripetal force must be provided by friction. Determine what centripetal force must be provided by friction to cause the flea to maintain the circular motion. So similar setup, we have a disc, and we have our little bug out here. There's my bug, and it's rotating around at 80 RPMs per minute. So let's start transferring some of this information here. So let's start with mass. So mass is 0.2 grams. So we want it in kilograms, need to divide that by 1,000. So I'm just going to leave it as 0.2 over 1,000 since I don't have a calculator handy at the moment. Kilograms. We're also given the radius in the terms of diameter, and we want it in meters. So 10 centimeters is 0.1 meters. Divide that by 2. So 0.05 meters would be our radius. Now the interesting part here is the RPMs. So 80 RPMs. So we know that we have a frequency. Frequency is how many revolutions per minute an object is spinning. So that would be a frequency. So RPM. Now that's not in our SI standard. We need to get it into hertz. And hertz is revolutions per second. So there are 60 seconds in a minute. So the conversion would be simply dividing by 60, and that would give me RPS, which is hertz, revolutions per second. 80 divided by 6, that reduces down to 4/3 or 1.3 repeated. So what information is given here? What are we dealing with? Well, I have a frequency, I have a mass, I have a radius, and what we're looking at, we know that the flea wants to fly off, okay? And this is where some confusion lies. We know force centripetal is technically always toward the center of the circle. So that means the force of friction has to oppose motion. Now, for those of you that are thinking, I've been on a spinning object before, and I want to be thrown outward, yeah, that's your tendency. You want to be thrown outward, and it's friction which is holding you in. So I'm going to have some people here that are going to draw their free body diagrams so that they can kind of wrap their heads around it. And I'm not a big stickler on this, but you need to be careful because you get into the pure physics. people are going to call you on that. You know the tendency is that force centripetal is to throw you outward off the edge of the circular device. So really the flea feels like it wants to fly outward. And it's friction, the traction between the feet and the disc that's keeping the flea on there. So a lot of people are going to say, and I'm going to put this in green, force due to centripetal should be pointing inward. So it's kind of a bizarre situation where force centripetal and force friction should technically be drawn in the same direction here. But for us this year, to simplify it so you can wrap your head around it, I'm going to be okay with you as long as you answer the first question on the test about which direction does it point, that you can draw it in the sense, in the way that it makes sense to you. So what I've got circled there is not technically correct. However, it allows your head to get around, wrap around what the situation is. So centripetal wants to throw you off the disc, friction's keeping you on. So that's what we're technically looking at. So that being said, the formula, force centripetal, you got frequency, so it's a dead giveaway. So we're looking at 4m pi squared, frequency squared, r. And now it's just straight substitution. You've done all the hard work. So 0.2 divided by 1,000, pi squared, 4/3 squared, and the radius is 0.05. So now it's just a plug and chug situation where you put it into the calculator, and you come out with approximately 7 times 10 to the negative 4 newtons. It's a friction, and we're going to say in, just because I went with my free body diagram. All right, so if you need to, okay, if it helps kind of make things make more sense for you, you can draw that centripetal force in the direction that you feel your body wants to go. And that helps sort of figure out which way the friction is going. But keep in mind, you get into if you take a pure physics course, it's going to be a no-no because force centripetal always points to the middle. So there's your kind of heads up or warning. Okay, so let's talk about a car traveling around a bank surface. So here's my surface. There's my 20 degrees. Here is my car. Make it a block. Coefficient of static friction. So mu s is 0.6. Why are we given static friction? Well, the car is moving, you say, but the car is moving in to the page. It's not moving side to side. So when you are dealing with sort of a two-dimensional situation, the car is moving, yes, in and out of the board. Okay, we're looking at the tail lights of the car. So it's going around the curve. We're looking at the tail lights. It's moving in and out of the board. However, the car is not sliding up and down the curve. So technically, in that direction, the red arrow I drew, it's actually stationary. It's not moving side to side. So that's why they have to give us that coefficient of static friction. What else is given here? Radius of the curve is the 200 meters. Determine the maximum velocity. So we are looking for velocity. That's our unknown. That a car can go around the curve safely. So what we got to do is we got to take it and look in terms of our forces here. So I'm going to draw all my vectors on. So here's my normal force, Fn. We got our force due to gravity, straight down. It's going to want to slide down here thanks to gravity. And our force of friction, and this is where things get kind of interesting. Our centripetal force, okay, points to the center of the curve. Our force of friction is helping keep the car from sliding off the ramp. So again, I am going to point force due to friction in this direction. All right, so there we are. So there is our force due to friction. That's holding the car on there because technically centripetal force is making you want the car to slide sideways, and it's going to be a component of the centripetal force. So let's call it the X, since that's the convention with FGX. All right, so let's look at the formula that's involved here. So we know that we're dealing with force centripetal. Okay, so our force centripetal, which is holding us on there. So I guess let's start with the balanced equation here. So FCX is going to equal force due to friction plus our FGX. So that is what is keeping this car from sliding up the slope. So the forces are balanced. So FCX is going to be, because we have radius and we're looking for velocity, it's going to be mv squared over r. So there's our left side of the equation. Our force due to friction is our normal force multiplied by mu, plus our FGX is force due to gravity, and if I remember, it should be sine theta. So here we go. I'm not going to substitute any numbers in quite yet. So mv squared over r is equal to mu. Our normal force, again, is force due to gravity, Fg cos theta, plus Fg sine theta. And if I go one more step of substitution here, I'm just going to get rid of the Fg's because I want you to see that Fg is mass times gravity, cos theta, plus mass times gravity, sine theta. Every term has a mass here, so the mass of the car does not matter for us here. Mass of car does not matter. I want to isolate for V, so I'm going to end up with V equals, so the R would have been multiplied up to this expression, cos theta plus G sine theta, and then I'm getting V by itself, so it'd be the square root. And yeah, you can common factor out if that makes it quicker for you. I just wanted to show you the steps here. So our radius is 200. Inside we're going to have, so I'll go square brackets just to show, 0.6, 9.81. I guess we're using 10. Make life a little simpler for ourselves. Cos 20 plus 10 times sine 20. Closing square bracket. Now we go through and do the calculation. When I complete that calculation, I get 42.6 meters per second. Okay, and that's a magnitude here. So I'll just put that in. So that's the magnitude. That is our maximum magnitude. So therefore, max velocity would be 42.6 meters per second, which translates to about 153 kilometers an hour. And there's our calculations for this particular vehicle. So the mass did not play a role. Now, I do talk about a satellite in orbit, and we talk about a little bit later on in more detail the gravitational potential. But just quickly going through it here, we're talking about a satellite here. It's always tangential that the satellite wants to travel. So if our satellite is right here as it's orbiting Earth, at every point in time, its velocity is tangential to its orbit. Now, if the satellite loses orbit, or if our centripetal force is exceeded, because centripetal force is what's holding this satellite in, okay, this would be the path. So centripetal force is holding our satellites in orbit. Okay? So that force centripetal is facing the center of the Earth, no matter where the satellite is in its orbit. So at any point in time, the satellite, we say, is always falling because its acceleration is toward the center of the Earth. Centripetal force. So if something changes where the satellite is given extra energy, which we'll talk about in later units, it may have enough energy to increase its force that would let it lose its orbit, and what would happen is the path would be in that particular direction. Same thing if you have a sling. When you're swinging the sling around and you let the stone go, not that many of us do that anymore, the stone goes in the direction that you release the sling. So that is the direction of the satellite's velocity. Same thing if you have something on the end of the rope and you're spinning it and the rope breaks, whatever's at the end of the rope will travel tangential to that circular path. All right. So homework. There's a handout for this particular section. There's a couple of questions that weren't in the textbook that I like. So you're going to have an opportunity to work through that tomorrow, and we'll see how that goes. If you have any questions, definitely there to give you a hand in completing that.